Hello Year 11, welcome to week 17. Just to give you a warning, this is a longer video. We are covering a whole section topic here on characters, images, sound and compression. So make sure you take your time, maybe do this video in two parts because we're covering a very important topic that will always come up in the exam in some way. Okay, so find revision sheet 4. We are covering the whole of the sheet today, so make sure you've got revision sheet 4 with you. And again, take your time with it, maybe do it in two parts if you need to. This section we are covering characters, images, sound, and also looking at metadata and compression, which is linked to images as well. One of these topics, something about them, will always come up in paper 1, so make sure you are ready. Okay, first topic, character sets. What is a character set? Well, just remember that everything on the computer is stored in binary, using binary numbers. We know this. Okay, so how do we store characters? How do we store words? Well, remember, a character can be anything. It could be letters, numbers, symbols in uppercase and lowercase. And the computer can't store these directly. So they have to store them as a binary number. Every character on your keyboard, including symbols, numbers, has a binary number with it. And remember, there are lots of characters on the keyboard, so a whole collection of these characters with their binary numbers is called a character set. A collection of characters and their binary representations or their binary values. So there's an extract of a character set with the basic letters on the keyboard, A to Z in uppercase, lowercase, and the symbols. And that is an abstract of the ASCII character set that we learned about. So to remember, how does it work? Well, when you press a key on the keyboard, a signal is sent into the computer that converts it into the binary number. The computer then looks up that binary number in the character set, it finds the letter or symbol, and it displays it on the screen. That all happens extremely fast. So the two character sets that we have learned about that you need to know. ASCII. ASCII is the most common used character set in English. It has the main characters in English-speaking languages, as well as some characters from European languages like accents, French and Spanish and things. Every character uses 8 bits, 8 ones or zeros to represent the code, and there are 256 different characters that can be stored in this character set, which is enough for all the English letters, numbers, symbols, and some European ones as well. ASCII, 8 bits, 256 characters. And the other character set we learned about was Unicode. The Unicode is much bigger. It uses either 16 or 32 bits to store every character, and it can store over 65,000 possible characters. That's enough for all major languages, even including ones with completely different character sets like Greek and Russian, and even space for emojis. So 16 or 32 bits per character and over 65,000 characters. On your sheet, complete this section now, please. What is a character set and what are 3 main features of ASCII and Unicode? Okay, check your answers. The main thing is you need to know the definition. What is a character set? A collection of characters and their binary numbers or their binary values or representations is the fancy word. ASCII, 256 characters, 8 bits per character, enough space for European languages. And Unicode, 65,000 characters, 16 or 32 bits, and it covers all major languages in the world, including emojis. Character sets done. Let's move on. Images. Now remember, again, computers cannot store images directly. The only thing they can use is binary. So everything on an image has to be stored in binary in some way. This is a high quality bitmap image. And if you zoom in, doesn't matter how high quality it is, eventually you'll see that the picture is made up of pixels, little squares of color. And a pixel is a single block of color in an image. It's short for picture element. But the main thing is a pixel has one single color. And a bitmap image is made up of lots of pixels all put together. Some other things you need to know. The dimensions of an image are the height of the image times the width of the image in pixels. If you multiply them together, you'd get the total number of pixels in that image. Height times the width of the image in pixels. So in this case, that'd be over 2 million pixels by multiplying them together. We also have the color depth, the number of binary bits used to store each pixel. So if I only use one single bit to store a color of a pixel, I can only have two colors because it's either a 0 or a 1. If I use 2 bits, there are 4 combinations. If I use 3 bits, there are 8 combinations. The more colors you needed, the more bits you need to store each pixel, but the larger the file size it gets. Most color photos are stored with 24 bits of color. That's 8 bits for red, green, and blue, and that gives you millions of different color combinations. So color depth, the number of binary bits stored for each pixel. And just to see it in action, there you can see 24-bit, nice color photo, and as we reduce that, the number of colors becomes less and less and less. The quality looks like it's getting worse, but basically the colors are just less. And the file size would also get smaller as I reduce them. Now have a look at this one here. This is not color depth. This is an example of resolution. The number of pixels in an image. The image on the left has got a lot more pixels. The pixels are smaller, so the quality looks better. The one on the right has less pixels. The pixels are larger, so the quality is less. However, the one on the left, A, would be higher resolution and a larger file size. So the resolution, the number of pixels in an image. Higher resolution, better quality, but more pixels and more data, so bigger file size. Lower resolution, less pixels, less data, lower quality, but lower file size. Resolution. And to see it in action, there's a high resolution image, 72 dpi or dots per inch. And as we reduce that, you can gradually see the quality getting worse and worse and worse because there are less pixels. The pixels get larger because there's less of them, to the point where the quality is very, very low. But the file size would be smaller. Okay, main points. Pixel, a single block of color. Dimensions, the height and the width in pixels. The resolution, the number of pixels in the image. And the color depth, the number of binary bits for each pixel. The more bits you have, the more colors you have available. Okay, on your sheet, complete this section please. Fill in with the information if you haven't done so already. And time to check your answers. As always, make sure you've got the detail. Bitmap, an image made of pixels. Pixel, a single block of color. Color depth, the number of bits for each pixel. The resolution, the number of pixels in the image. And the dimensions, the height and the width of the image in pixels. Okay, while we're on the topic of images, let's just remind what metadata is. So remember, if you right-click on an image, as we did in practical in class, you will see all the information under the Properties tab. It shows you all the information that's stored with the image or the file. So metadata is the extra data that's stored with the file that gives information about the file's properties, the information about the file. Some of those details are essential. You have to have them in order to show the photo. Things like the file format, if it's a JPEG or PNG. The height and the width, the dimensions, you have to have it. The color depth and the resolution. Without those informations, you cannot show the image on the computer. However, there are also some non-essential things like the camera used, the settings of the camera, the name of the person who took the photograph. Those are not essential, but you can store it with the image as well. So So just an example there, you can see a high quality photo that was taken. We've got the information on the left that is essential, like the dimensions, the resolution and things. And on the right, you've got details such as the camera that was used, the title of the image and things like that. Those are the non-essential information. So information that you need to know, essential and non-essential. And metadata is the extra data that's stored with a file that gives information about its properties. On the sheet, quickly make a note of that now, please. And again to check, metadata, the extra data stored with a file about its properties, essential, things like file format, dimensions, color depth, resolution, and non-essential, make sure you can know some examples, things like camera settings, name of creator used, etc. Okay, let's move on to sound. Sound, now this is one that people forget a lot of, so it's very important when you remember some basics. All sound that we have in the real world travels in waves. It is analog. The sound goes up and down in waves, depending on with different frequencies and things. You learn about that in physics and things. Analog sound. So we cannot store that on computers. So we have to have a way of converting that analog sound wave into a digital format. And that process is called sampling. The process of converting sound from analog, the wave, to digital by measuring the amplitude or the height of the wave and recording it as a binary number. So in this example, you can see the dots there. The height of the wave, the amplitude, is measured at regular points, at regular intervals, and that number is then stored as a binary number. So as I go here, you can see the different readings of the wave that can be stored as a binary number. And that process is called sampling. The gaps in between each sample are called the interval. The gaps in between each sample that's taken. So it may be every 5 milliseconds or every 10 milliseconds. That is the interval. And then we have the sampling frequency. How many samples, or the number of samples taken per second. The more samples, the more measurements of the wave, the more closer to the original sound it will be. But the more data, the more space needed to save the bits of data. So the number of samples taken per second. The more samples, the closer to the original it will sound. As well as how often you sample the wave, the sampling frequency or rate, another factor is how much detail you take about each sample. So you can have thousands of samples per second, but if you don't take much detail about it, it's not going to sound very good. So the other thing is the sample depth or the sample size. So in this example on the top there, we've got a low sample size, only 2 bits recorded for each sample. Not much detail about the sample. In the bottom, we've got 8 bits recorded for each sample. Which one's going to be better? Well, of course, the bottom one, because there's more detail, there's more information for each sample. So this is called the sample size or the sample depth, it may be referred to. How much, the number of bits used for each sample. The more bits used for each sample, the closer to the original again it will be, the better the quality. But the file size will be larger as well, because there's more ones and zeros, there's more binary data being stored. Sample size or sample depth. And finally, once you have those two things, the sample frequency and the sample depth, you can work out the bit rate, the number of bits used per second of audio. By multiplying those together, the sampling frequency and the sample size, you can work out the number of samples per second, the bit rate. It is possible they could ask you to calculate in the exam. They might give you the information and ask you to work at the bit rate. So you multiply the sample frequency by the sample size or the bit depth together. It's important to know how to do that for the exam. Okay, on your sheet, please, fill it in, and then check your answers on the next sheet, on the next slide. Okay, checking answers, as always. Sampling, converting audio from analog to digital, that's 1 point, by measuring the amplitude of the wave, 2nd point, and saving it as a binary number. The only bits missing there, it should be on there, is you do it at regular intervals, at regular points in time. Apologies, can you add that on, please? The sampling interval are the gaps in between each point where the sample is taken. The sample size is the number of bits used for each sample. The frequency is the number of samples per second. And the bit rate is sampling frequency times sample size. You multiply them together to give you the number of bits per second. And the very last thing for us to revise and to know for this exam for data representation is compression. Now for sound or for images, they could be quite large. So why do we compress those files? We compress them to make the file sizes smaller, but still trying to keep the image as close to the original as possible, so it's still good enough to use. It means that files will take up less storage space. It means it makes it easier to stream or download files from the internet, uses less bandwidth, and it's much easier to send content via email or attachments because their file sizes are smaller. So compression. There are 2 types of compression we looked at, lossy and lossless. Now remember, lossy works by permanently removing data from the file, and the file is smaller because there's less bits. Where lossless, the data is temporarily removed, but you can fully restore the image or the sound clip when you open it again, when it's uncompressed. So you can get all the data back again. Lossy, permanently removing data from the file, but it's permanent. You cannot get the full original image back or sound clip back. It can be used on sound and images, but it cannot be used on text or software. Why? Because if you compressed text and removed data from the file, it would not work anymore. You wouldn't make sense or the file would not run. You get syntax errors. So you cannot permanently delete things from a text file or software. It doesn't work. However, good things about it, it does greatly reduce the file size, there's less bandwidth, and it's very commonly used. However, you cannot get the original quality back and it cannot be used for text or software. And common types are things like MP3, JPEG, AAC for audio, the main ones. And how is that different to lossless compression? Well, lossless, remember, it is only temporarily removed. You do not lose any quality in the final thing. It can be fully restored at the end. And it can be used on text and software because you're not actually deleting anything. Cons, however, there's only a slight reduction in file size. It still takes up quite a lot of space. Common file types are things like TIFF, PNG, or FLAC for audio. Okay, on your sheet, lossy and lossless, making sure you've got your notes and checking them on the next section. Okay, lossy, compression that works by permanently removing data, can greatly reduce file size. However, the file cannot be fully restored, and it cannot be used on text and software. Lossless, temporarily removing data, and it can be fully restored when it is opened. No reduction in quality and can be used on text and software. However, it's only a slight reduction in the file size. Okay, that's a lot being covered today, year 11. Make sure you have your notes, make sure you fully understand, rewatch the video if necessary. And once you are done, have a go at revision quiz 17 on LangCube, which checks the content for this as well as some previous revision topics we've done. Good luck, and I'll be checking this in lesson. See you soon. Bye.